Okay, so we're going to look at problem 1715. You'll find it on page 1214 in your book. So the givens are mass of gear A is 1 kilogram. K, which is the radius of gyration of A, is 0.03 meters. Okay, it's giving it to us as 30 millimeters, but we know that we need to use meters anywhere that we're going to be using, values, because we need things in meters per second, for instance. Our radius of A is 50 millimeters, 0.05 meters. Okay. Next, we have mass of gear B, 4 kilograms. Okay. Radius of gyration of B, 0.075 meters. And now B has two radiuses, okay? The larger on the outside that engages with A, I'm going to call that radius B1. And the smaller one that engages with gear C is going to be called radius B2. So RB1 is 100 millimeters or 0.1 meters. RB2 is 50 millimeters or 0.05 meters. Okay. And then we have gear C. So the mass of C is 9 kilograms. Its radius of gyration of C is 0.1 meters, 100 millimeters. Radius at C is 150 millimeters or 0.15 meters. And then the moment at C, capital M sub C, is 4 Newton meters. Okay. Now, we need to find theta A in revolutions at WA equal to 300 RPMs. Okay. All right, so that's what we're given. Now, approach. We're going to use the work energy theorem. Okay. Work energy. So we know that T1 plus work is equal to T2. Our initial kinetic energy is 0 because we're starting from rest. Okay. Now, as we look at this, let's expand the work and the kinetic energy. So we know that our work, this is rotating, is going to be the moment at C times the number of revolutions or the radians at C, the angle for which it goes through, is going to be equal to, because that's where the work is going in, it's going to be equal to 1/2 moment of inertia at A times the angular velocity at A squared plus 1/2 moment of inertia at B times angular velocity of B squared plus 1/2 moment of inertia at C times angular velocity of C squared. Okay. Now, as we look here, I always like to kind of tick off the things that are relatively easy to get. As I look at this problem, the easy gets are going to be the moments of inertia of each one of those gears. Okay, now they gave us radiuses of gyration. So when they give radius of gyration, that means that it's not a solid disc, and it's not, because it's a gear. You have the cutouts, of the teeth, so you can't use the cylinder disc really accurately. So we're going to use the general where we need to take the mass times the radius of gyration squared for each one. So I'm not gonna calculate each value, but basically our moment of inertia A is gonna be mass of A times K of A squared. Moment of inertia B, mass of B times KB squared. Moment of inertia C is mass of C times KC squared. Okay, so you're going to get each one of those values and you'll have an actual number for each. Okay, now this is where inside the problem, I was holding 4 and 5 decimal places, honestly, because there's kind of that. All right, so don't round to 1 or 2 decimal places. Okay, hold 4 and 5 through here. Otherwise, you're going to have your numbers are going to be way off because there's steps here now that we're going to continue to go through. So moments of inertia. All right. The next thing you're going to do is angular velocities. Oopsie. And those are our W's. Okay. Angular velocities. Now, we know what the angular velocity of A has to be. It's in RPMs. Okay. So we can say angular velocity of A is going to be equal to 300 revolutions per minute, but we've got to convert that to radians per second. Okay. So you want to get WA in radians per second. So that's going to be something that you have to do. You have to do that conversion. Now, as we look at the angular velocity of B, okay, the angular velocity of B is tied to A because it meshes with A. And as we know, velocity ratio, we can figure out between two gears that are in mesh. So if you recall, down at the bottom of our equation sheet, velocity ratio between two gears, we can use any one of these values depending on the information that we're given. So in this case, we know the radiuses, okay? Now, you have to know which is the 2 and which is the 1. 2 is going to be the driven, or in our case, it's going to be B because it's the larger of the two, because A is going to be our input. And then the smaller of the two is going to be the driver. So that means it's going to be the radius of B over the radius of A. So we can say that WB times the radius of RB1, which is the radius that engages with A, is going to be equal to WA times the radius of A. Okay. We can then say that WB is equal to small r, RA, RB times WA. This is that velocity ratio. Okay. Now you're going to solve for WB, and you're going to get a value in radians per second because this is your radians per second is going to be the value that you put in there for A. Okay. Same thing for WC. We can say that WC times RC is going to be equal to WB. Now be careful because remember, on the same shaft on B, there's a, if you would, a forward gear that engages with C, and its radius is different than the one that engaged with A. So you need to multiply this by RB2. Okay, and up here, RB2 was different than RB1. Okay, so we can say that WC is equal to RB2 over RC, okay, times WB. Okay, so now your WB you're going to put down here, and then you're going to have your WC in radians per second. Does that make sense to everybody? Okay. Now, as we go back up to this equation, for each one of these at this point, then we have moment of inertia for each one from here, right? We have our angular velocities here, okay? So we have the whole entire right-hand side of that equation checked off. The moment at C is right here, 4 Newton meters. So that's checked off. Your only unknown then is going to be your theta at C, okay? Theta at C. So you're going to solve for theta C, okay, in the work energy theorem. So I'm just going to rewrite that here so that it's that theta C is going to be equal to, you're going to have your 1/2 IAWA squared plus 1/2 moment of inertia B times WB squared plus 1/2 IC times WC squared, all over capital M, which is the moment at C. You know all of these things. Your only unknown is going to be theta C, okay? Now, that's not what we're looking for. We are not looking for theta C. We need to know what theta A is in revolutions, okay? I'm going to give you this hint, and then you guys are going to finish this up. You're going to take the theta A. It's going to be equal to your train value times theta C. Train value, remember when we have more than one gear in mesh, so we have 2 sets of gears in mesh here. Train value is taking the individual velocity ratios between, if you would, A and B and C, the individual velocity ratios, you're going to get a train value. Okay, multiply those together. You're going to take that train value, you're going to multiply it by what you had there. And then remember, this value coming out of here is in radians. Theta A, you need to have in revolutions. So there's going to be a conversion there that you have to do. Okay. So are there any questions on this process? Again, I'm trying to give it to you so that you then have a good, steps to go through that makes sense. But now I want you to kind of go through and do the work of adding in the numbers and making sure that you can get the final answers. But this is the process that you want to follow. Okay, if there aren't any questions, what I'm going to do is I'm going to stop the recording.